what I'm going to do now is give a short introduction, and then we'll hand over to Caroline to give the talk. So Caroline did a first degree in Aberdeen in chemistry with German, and then a PhD in solid state chemistry, also Aberdeen. Then moved to Sheffield in about 1999 to work in Tony West Group. She did a PhD with Tony West in solid state chemistry. So that was in engineering materials, and interestingly, Caroline actually participated and won the heat of the young person lecture competition for the Sheffield Metallurgical SMEA. Yeah, so people who are aware of the SMEA might remember people like Ken Rydell and so on. Then moved to the Natural History Museum in 2002 to work as an X-ray lab manager. So they do lots of good science at the Natural History Museum, as well as having a museum for you to go and have a look at. Then moved to chemistry in Loughborough in 2007, and then moved to where she currently is. Yeah, Edinburgh. Right. So what I'm going to do now is hand over to Caroline. So thank you very much for agreeing to do the talk at relatively short notice as well. So over to you. Thank you very much.
Okay, I'll share my screen. Hopefully get the right one. Right, so thanks for the invitation and the introduction. It's a great pleasure to chat to you this evening about some of the research that we do at the University of Edinburgh. So just as a kind of general overview about the research that goes on in my group, to kind of summarise it, I would say we do materials chemistry for environmental applications. So as Simon mentioned in the introduction, I spent part of my research career at the Natural History Museum, so my research definitely has a kind of mineralogy flavour to it. And indeed, many of the projects that are carried out in my group begin life as characterisation of some natural samples. So we're often targeting specific minerals, maybe because they are good at remediating toxic elements such as arsenic or chromium or uranium, and we want to look to see how stable they are in nature. Or maybe we're actually trying to do the opposite and break them down and extract a critical element. So for instance, at the moment we have projects about lithium ore materials. So can we find ways to extract the lithium? So after characterising the natural samples and picking our minerals of interest, we then go on and do careful, controlled laboratory studies to try and make synthetic analogues. And then from that, we can look at formation processes, which might help us to understand how they form in nature, and then move on and look at stability and property measurements. Most of my projects do a lot of characterisation and primarily diffraction. That's my favourite technique, especially X-ray diffraction. So we do a lot of lab studies using X-ray diffraction to identify the crystalline phases present in materials, and we do structural studies as well. We use spectroscopic techniques to complement our diffraction studies, so IR and Raman, for instance. We'll often use thermal analysis, quite a lot of thermogravimetric analysis, because many of the mineral phases are hydrous, contain water, and also we do a lot of microscopy as well. And one thing that we're really interested in is trying to understand the properties and stabilities of these minerals. So we will try and monitor that in situ by developing experimental cells, and we do a lot of that work at central facilities. So we use diffraction techniques either with synchrotron, so this is the diamond light source at the Harwell Science Campus, or we sometimes use neutrons as well. And using these advanced techniques, we can monitor the diffraction patterns as a function of maybe temperature and see how the diffraction pattern changes, and that gives us an idea about their stabilities. So I'm going to tell 3 stories this evening. The first 2 are focusing on mineral phases that we think have potential remediation material applications. So one is this copper uranyl, put the laser pointer on, uranyl arsenate phase or phosphate phase called metatorbernite. Then Ettringite, which is a mineral phase, a calcium aluminium sulfate hydrate phase, which actually also forms in cement. So that links with the final talk that I'm going to do on sustainable cements. Okay, so the first topic tonight is going to be looking at metatorbernite-type minerals. So these are copper uranyl phosphate minerals. We want to investigate the environmental stability and look at synthetic analogues. So this project started when I was still at Loughborough, and we're part of a consortium that was looking at the fate of radionuclides in the surface environment. We were mostly interested in uranium in our project, and our study focused on the South Terrace mine in Cornwall, which was a disused uranium mine, and in fact it was the only mine in the UK to be solely mined for uranium. But it's been out of production for a long time, in fact since the 1930s, And since then, the site's been left largely untouched. And here's an aerial photo. It's actually a radiological map. So you can see it's surrounded by green fields. And then you have this sort of purple area here, and then the hot spot, which is the spoil heap in the disused mine, where most of the uranium still exists. So this site has been worked on a lot, especially in the early 90s, and it's shown to have still a large amount of activity left. And it would seem that the uranium is not particularly mobile, and it's mostly either present as the primary ore, which is pitch blende, so uranium oxides, or as a secondary mineral, which is formed through weathering processes. And this is where this phase metatorbernite is mentioned as being present. And this copper uranyl phosphate phase is said to be stable under circumneutral pH conditions. So with this in mind, it was a thought that perhaps these kind of phases could be used to remediate uranium and lock it up. So the start of the project involved going down to Cornwall with some buckets and shovels and getting some samples from the spoil heap and the farmland surrounding the spoil heap, and then bringing them back to the lab. And we started off by looking at the soils and measuring their activity using a Geiger counter, and then we subsampled into areas of high activity. Then we went to my go-to technique, which is actually powder diffraction, to try and work out what phase or phases were present in these highly active subsamples of the spoil heap. And this is where we noticed the presence of this metatorbernite-type phase. However, in about 50% of the patterns that we analysed, we always saw a shift in the peak position. It never really quite matched up ideally with metatorbernite patterns in the database, and it was always shifted to slightly lower angles. So we thought that this must suggest that it contains a foreign element, something that's not phosphate, that's causing the unit cell to expand, and hence a shift in the diffraction pattern. Because it's Cornwall, there's lots of interesting elements present, and arsenic is one of those. So we were suggesting that perhaps some of the phosphate has been replaced by arsenate. There's a known analogue to metatorbernite called metazunorite, which is a copper uranyl arsenate phase. And these are known to be isostructural, so they have the same structures. And both metatorbernite and metazunorite are part of the autunite family, which is a calcium uranyl phosphate phase. And these are basically layered structures. We have uranyl phosphate or arsenate layers, and then between the layers we have cations or waters situated. So here is a picture of metatorbernite. So this is a nice green platy crystalline sample, and this is a representation of the structure. So we have uranium in green, it's octahedrally coordinated, and it shares corners with tetrahedral phosphate, forming these sheets. Then between these uranyl phosphate layers, we have the copper ions, and these link octahedrally, and they're known as Yan-Teller distorted. So because of the electronic configuration of the copper 2+ ion, we find this distorted octahedral coordination with longer axial bonds than equatorial bonds. And then we also have lots of water molecules situated between these layers. So the copper is kind of holding these uranyl phosphate sheets together. So we started off by doing some synthetic studies. We made samples of metatorbernite and metazunorite, and then we wanted to investigate the solid solution formation. So can we replace some of the phosphate by arsenate and make intermediate compositions between the two end member phases, so the pure phosphate and pure arsenate? And indeed, we were able to do this, which we confirmed by powder diffraction techniques. So this is some high-resolution synchrotron powder diffraction data that we collected at the diamond light source on their high-resolution beamline I11. So from the phosphate analogue to the arsenate analogue at the top. Oh, what's happening? Hang on, sorry, something's frozen. And you can see here actual shifts in the peak position. So the phosphate here, and the peaks shift to lower angles as we move to the arsenate. So this is what I was saying. The arsenate ion is bigger than the phosphate ion. We see an expansion in the unit cell, and this causes the diffraction patterns to shift to lower scattering angles. So by eye, there looks to be a change, but we confirm that by refining the unit cell parameters. So it's a tetragonal system, so we have two parameters we can refine, A and C. And we can plot those parameters as a function of the composition. So from the pure phosphate to the pure arsenate, and we see an expansion in A and C, and it's linear with A within errors, but there's a bit more scatter in the C parameter, and we suggest that this is to do with a variable water content. Because the water molecules are between the layers, we get a bit of variability in the C direction. So now we have our database that we can go and use to match with our natural samples. So the black pattern shows a diffraction pattern of a soil sample matched to one of our synthetics, and we found that the composition is likely to be about 25% phosphate and 75% arsenate. And we can refine the unit cell parameters and plot it on that graph as well. But it's a good way, when you have that linear trend with composition, of being able to predict what the composition might be. And we used elemental analysis, so inductively coupled plasma optical emission spectroscopy, to look at the ion content and confirmed this to be the ratio. So as well as unit cell parameter data from diffraction patterns, we can also look at the crystal structures. So here we have two reported crystal structures, one of metatorbernite and one of metazoonerite. And they're the ones that we could find in the literature were suggesting that the structures were different between the two compositions. So here we have copper on a twofold site, so we have two copper ions in the unit cell. The uranium and phosphorus are ordered on two twofold sites, so 1 and 2 for the uranium and the same for the phosphorus. And we kind of think of this as a more ordered structure, whereas the predicted or proposed structure for metazoonerite is more disordered. So here we have copper, and you can see there are now 4 sites in this particular unit cell, but it's only half occupied. And the uranium and phosphorus are disordered over 1 4-fold site each. Most of the structural models that have been published have been defined using X-ray diffraction techniques. And actually there is a slight problem, or actually a large problem, when we use X-ray diffraction to try and monitor or analyse the structure of something like copper uranyl phosphate. So just as a refresher, X-rays interact with clouds of electrons. So the heavier the element, the more electrons it has, the stronger it will scatter X-rays. So we have uranium in this compound, which is going to be a very dominant scatterer of X-rays, and that means it's harder to locate the light elements such as hydrogen and oxygen. So to really monitor and understand the water positions in this phase is really difficult, and in fact a lot of the models published don't have hydrogen ions in their structural models. So we turned to a different diffraction technique, neutron diffraction. Neutrons interact with atoms differently. They interact with the nuclei rather than the electrons, and there's actually no correlation between the number of electrons, or Z, the atomic number, and the scattering length. And in fact, things like hydrogen and oxygen are very good scatterers of neutrons, so it makes them neutron diffraction a really useful technique when you're studying crystal structures that consist of heavy and light scatterers of X-rays. So we very successfully carried out a structural study, and Fee, who's actually in the meeting this evening, worked really well, really hard to analyse the data and came up with a nice structural model, including the hydrogen bonding network in metatorbernite. And we combined this with a modelling technique known as AIRS, ab initio random structure searching, and we found very good agreement between the two techniques, so we're very confident in this structural model for metatorbernite. Now we are able to understand the hydrogen bonding network, and we can show how the hydrogen bonds cement together the sheets and the layers. And this then allows us to start thinking about what's going to happen if this material dehydrates. So if we heat it up, which water molecules are we going to lose first? So it gives us some information about the stability of these materials at high temperatures. So why would this be interesting to do variable temperature studies? So they're hydrated minerals, they have a lot of water. So what will happen if we heat them up and the water is lost? And this becomes relevant when we think about where spoil heaps might exist in the world. So in damp, wet UK, Cornwall, probably we're not going to get very high temperatures in these spoil heaps, but somewhere like Namibia, where this picture is from a uranium mine there, the spoil heap temperatures can be greater than 100 degrees C. So we want to study what happens to these materials at high temperatures. So we used several techniques, thermogravimetric analysis. We also did variable temperature studies using synchrotron X-rays and neutrons. The thermogravimetric studies showed the decomposition pathways or dehydration pathways were actually different for the two phases. So with metatorbernite, we have one large weight loss here up to about 150 degrees C, where about 6 water molecules are lost. So we can use the weight loss to predict how many water molecules are lost at each event. We then lose another 1 water molecule up to about 270, and the material becomes anhydrous, so all the water molecules have gone by nearly 500 degrees C. Whereas for the metazoonerite phase, which actually starts off as a higher hydrate, so what we found is when we make these samples and we use a precipitation method, that the initial phase formed in the arsenate system is a higher hydrate, which is actually called zoonerite and has 12 water molecules in it. So zoonerite eventually dehydrates by about 100 degrees to metazoonerite. We then find that there are different steps in the dehydration process and it becomes anhydrous at slightly lower temperatures. So we want to monitor these changes structurally and use diffraction techniques. So we went to and did some synchrotron X-ray studies, and you can see as a function of temperature, the diffraction patterns look very different. So that's indicating something is happening to the structures. And we were able to show perhaps 4 different types of phases forming by analysing the unit cell parameters excuse me, from the XRD patterns. To study the structures in more detail, we did some neutron diffraction studies, and we could see here when the metazoonerite and metatorbernite dehydrate and form these different phases, which we've labelled A, B, C and D. And again, lots of careful analysis of neutron data, we've come up with a predicted dehydration pathway of these two uranyl phosphate, uranyl arsenate phases. So we start off with our metatorbernite phase, and at 110 it's going to a tetrahydrate, 150 is going to a monohydrate, and then about 450 we think it's probably anhydrous. The data, as you maybe saw in the last slide, at higher temperatures the peaks are broadening, it's becoming much more disordered in nature, almost amorphous, so it gets more challenging to extract structural information from these poorly diffracting phases. We have some partial models anyway to give us some ideas of what might be happening. However, you might notice that dehydration pathways here are not correlating fully with the thermogravimetric analysis results. So this is really partly to do with different heating conditions. So in TGA, you heat your sample at a constant rate and you monitor what happens. Whereas for the neutron diffraction studies, we heat and we have to hold it at temperature for several hours to collect the data. So obviously the two types of heating are very different. And also the sample size. So whereas we'd use maybe 10 milligrams to do TGA studies, we actually need about 10 grams to do neutron diffraction studies. So there are obviously differences here. But we're very confident in the new models that we've developed from our neutron diffraction studies. And the same with metazoonerite. But here it goes from the 8 hydrate to the pentahydrate, then to a tetrahydrate before it becomes anhydrous. So the dehydration pathway is different to metatorbernite. So the composition is impacting on the stability of these phases. So just to round up the first part of my talk, we've shown that we can make a complete solid solution between the two end member phases, metatorbernite and metazoonerite, and we use that information to analyse some natural samples that we collected. We've developed some new models for the phases using a combination of neutron diffraction and modelling technique. And then we've gone on to look at variable temperature studies, and through understanding the hydrogen bonding, we can look at how the material starts to dehydrate as a function of temperature. So the next steps in this project are really trying to look at this material as a remediation material for uranium, for instance. So there are reports in the literature where we have permeable reactive barriers that contain things like apatite, so calcium phosphate type phases, that react with plumes of uranium and form autunite type phases. So that's fine if it's a liquid waste stream, but what about solid waste streams? So this is something that we're developing a lot in the group at the moment, something that's really new and exciting, using mechanochemical methods for synthesis of these phases. So simply grinding or milling reagents together, and we've successfully been able to form metatorbernite. So the next part of my talk is going to stick with the remediation theme, but this time move to a different mineral phase called Ettringite. So Ettringite was introduced to me when I was in Sheffield quite a long time ago, as Simon reminded me, and it was Professor Sharp, who I know is in the meeting today, that I have to thank for my love of Ettringite, and I still love this mineral phase. So it is a mineral, a very pretty mineral. There was lots of nice specimens at the Natural History Museum. It has an ideal composition, calcium and aluminium sulfate hydrate. As well as being in a mineral phase, it's also an important product, early hydration product in Portland cement. And as well as forming in early hydration stages, it also forms later on in cements called delayed Ettringite formation. And this is detrimental to the cement because it causes expansion and cracking. And there's another closely related mineral phase to Ettringite known as thomsite, which is a silicon carbonate sulfate phase. And it also can cause problems and is detrimental to the integrity of cement phases. So Ettringite is a great mineral family to work with because it has such a versatile structure and it can accommodate a range of different cations and anions. And because of this, it's been thought of to be used to encapsulate waste ions, and there are some reported studies that have successfully shown formation of Ettringite to remove aluminium and arsenic from wastewater by precipitation methods. So the structure of Ettringite, some pictures here. We have aluminium, which is octahedrally coordinated, so it's these purple features here that run down the C-axis, and here is an AB projection, so we're looking down the C-axis here. We can see these aluminium octahedra are surrounded by the calcium ions that are then surrounded by water molecules. So we form these cation columns, and then in between the cation columns we have the sulfate and water molecules between these channels. So we did some work a few years ago looking at analogues of Ettringite replacing the aluminium for different ions. So natural samples that I studied often contained iron or manganese, which can replace aluminium, and we made pure iron and manganese end members, as well as replacing aluminium with gallium. You can make a thomsite type phase, and we also made a tin version of thomsite as well. There are also studies in the literature where sulfate is replaced by a whole range of different anions. The ones we were particularly interested in were chromate and selenate. So the PhD project by one of my group, Rebecca Ray, was focusing on chromate and selenate. We were particularly interested in chromium. A colleague of ours in geosciences in Edinburgh has a project looking at contamination of chromium in a burn in Glasgow. And this has come from an old chromite ore processing plant that closed down, I think, in the 60s, but it is causing and still causing problems in one of the burns that actually ends up flowing into the Clyde. So it's a real problem close to home. So if you're going to try and remediate chromate and selenate from wastewater, we need to think about a process that's going to be cheap, simple and scalable. So how can we incorporate these waste elements, so the chromate and the selenate, into a material that can then be stabilised? Often waste is incorporated into a cement matrix. So could we think about using clinker phases, so the cement powder phases, the calcium silicates or calcium aluminates or calcium iron oxide phases, could these be starting reagents in this process? So we started by looking at this calcium aluminate clinker phase, which is known as C3A, and reacting it with different solutions of sulfate, selenate and chromate, and trying to work out what phases form. And the various conditions that we used, we varied time, concentration, which I'll talk to you a little bit about tonight, but also temperature and solid to liquid ratio need to be considered as well. So some of our preliminary results, I'm just going to focus on the chromate type phases that we've been investigating. So again, this is some data we collected on I11 at the diamond light source, so high resolution synchrotron data. And we found the formation of a chromate version of Ettringite after about an hour. We could see very small little bumps appearing. This became more evident after about 6 hours. So here we have chromate, but we have some other peaks appearing that we were able to identify as something called a monochromate phase, which has this predicted composition here. So the monochromate phase is something that's analogous to the cement system, where ettringite will further react to form monosulfate phases in cement. So this kind of process is known. And after a longer periods of time, so 24 hours and up to a month and a week and a month, we could see quite clearly that the product forming was monochromate, which was picking up the chromium from the solution. And we also found evidence of a calcium chromate phase, which is analogous with gypsum, calcium sulfate hydrate. So because we have high resolution data, as well as just identifying the phases that are present, we can actually do some modelling of the data and do quantitative phase analysis, so work out the proportions of each of these crystalline phases that are present. To do structural modelling, you need a model of the structure, and this is a bit tricky to start with for our analysis of the monochromate sample, because the model that was in the literature was, oh, my laser pointer's done something funny, was not actually very good. Sorry, that's it. So Rebecca worked hard and managed to build up a model. So we have this layer here, so calcium aluminium layers, and between the calcium aluminate layers we have the chromate anions and water molecules, and it's a very disordered structure. But with this structural model, we were able to carry out our phase quantification, and we could see that as the reaction progressed as a function of time, the amount of the clinker phase as calcium aluminate decreased, and the amount of ettringite started to increase and then decrease after about 1 day, whereas the monochromate phase increased all the way up to a month. Sorry, my computer is now frozen. Yeah, okay, so we were able to do our phase quantification and show the proportions of the phases changing as a function of time. So as one is decreasing, the other one is growing. We also monitored what was happening in the solution. So we'd made up solutions containing sulfate or chromate in this case. So we looked at the chromium concentration also as a function of time, and we could see that it decreased. And in fact, when we were using concentrations which were in the order of what we find in nature, so 0.01 molar solutions, after about 1 day, basically we couldn't detect any chromium above the detection limits of the instrument. So at low concentrations, this method is really effective at moving chromium from solution. So as well as doing things, so we were basically stopping the reaction, I think I forgot to say that, stopping the reaction at these times, filtering the solid and doing our analysis ex situ. But what we really like to do is try and monitor this in situ. So again, this was using the synchrotron source at Diamond, and this is Rebecca, who's the chromate girl, and this is Fee, who's the uranium girl, and they came to Diamond and helped with these experiments. So we had a little flow cell. Now not got the laser pointer on. A flow cell, which is basically a small capillary packed with the calcium aluminate. Then we pumped our nice yellow solution through the solid phase, and then we collected X-ray data as a function of time. We tried to use this flow system. So if you think about the permeable reactive barrier picture that I showed a few slides ago, it was a plume of liquid pushing through the solid phase. So this is kind of what we're trying to replicate here with the chromate system. So we were able to collect data sets starting about 30 minutes. Unfortunately, it was quite an involved job setting the flow cell up and ensuring there were no leaks. So actually, by the time we got everything ready to start the experiments, the reaction had already begun. And we think that we probably missed the early stages of this process. We were only ever able to see the monochromate phase present, and the reaction did not seem to be progressing after several hours. And we think it's probably because the solid phase is not being exposed to new liquid, so there's not fresh surfaces that are reacting with the chromium, so we're not seeing any further reaction. And when we compared it with some ex situ samples, we were seeing different phases present. So that's something that we're going to hopefully try and develop with new designs of the flow cell. So just to sum up the parts about the Ettringite project, so we were able to see chromate Ettringite forming, which is what we were hoping would happen when we reacted the calcium aluminate with the potassium chromate over a few hours. But then we showed that Ettringite would then convert to these monotype phases, which mirrors what happens in cement hydration processes. So as the amount of chromium in the solution is reducing, we see this conversion happening. So these results are showing that the formation of these Ettringite type and monotype phases do have the potential to remove toxic ions from waste solutions. And we really need to think about improving our experimental setup to do these in situ experiments. So again, the next steps with this project are really trying to see, could this be something that could be scaled up and used in the real world? And also thinking again to these solid waste streams. So although the chromium contamination that we were shown is in a burn in Glasgow, there are lots of solid chromium contaminated sources around the old works in Glasgow. So there are definitely solid waste streams there that need remediated. So again, could we think about using these mechanochemical type methods to form Ettringite phases? So they have the advantage that you're not having to put things in solution and potentially creating another hazard, another risk. Keeping everything in the solid state could be advantageous. Okay, so the final part of my talk is going to be looking at sustainable cements. There's a bit of an Ettringite link here. And this is a collaboration that I have with some colleagues in Brazil. So Professor Sandro Marden Torres's group and Williams, who I think is in the call, it was his PhD study. So this is part of his work that I'm going to present to today. This is actually a picture from his defence a couple of years ago. So why are we interested in this project? Well, as everyone knows, CO2 production in cement is a big problem, and we need to look at ways that we can reduce that. So what are the strategies? Well, one of those would be to use alternative fuels. So if we build this into a process, we're not having to rethink the design of a cement plant, for instance. It can be quite easily adapted to look at using different fuels in the kiln to heat up the raw materials and make these clinker phases. But what are the possible drawbacks and concerns? And this is what we've been thinking about. If we were to use different fuels in the kiln, could this introduce foreign ions into the system? So could the clinker phases, so these calcium silicates or calcium aluminates or calcium ferrite phases, incorporate other ions? And would this then impact on the reactivity and sustainability and durability of the end product of cement? So the aims of Williams' project were to look at possible interactions between impurities coming from the fuel sources during this clinker production, and we focused primarily on the main clinker phase, this alite phase, which is calcium 3 silicon O5 or C3S. We wanted to look at the crystal structure in more detail, model it as a function of these impurity ions, and then look at the cement properties. So monitor these, for instance, hydration processes. Would they change as a function of the foreign ions present? So to start with, we used XRF techniques to look at the elemental composition of our clinker samples. So I think many hundred, maybe or more, samples were analysed using XRF to look at the elemental composition. And we focused on magnesium and sulphur in the clinker samples and plotted the composition as a function of magnesium oxide and sulphur oxide. We then targeted specific samples that had high, low or medium amounts of sulfate and magnesium oxide in them to do further analysis. So this is William here and Rebecca again. So Rebecca's helped a lot out with beam time on the I11 beamline at Diamond. So to start with, we were doing our phase identification and modelling of the samples to work out what phases are present in the clinker. So they're notoriously very complex materials. So using high resolution techniques enables us to be more confident that we're identifying and modelling all the phases that are present. And we could easily see the alite phase present, and indeed two different polymorphs of alite, another calcium silicate phase belite present, the calcium aluminate phase that we used in the chromate project, C3A present, along with ferrite, which is a calcium iron oxide, and periclase, which is magnesium oxide. So we did a lot of phase quantification, and we were looking at changes in the proportions of the phases identified as a function of the sulfate content, for instance. We always found that alite M1 was the main polymer, so this green band here, but we could detect another alite polymer present as well, M3, and B-lite, which is C2S, another calcium silicate phase, we could also identify the presence of two polymorphs. And we found that the amount of M1 decreased as the amount of sulfate from the fuel content increased. So just to summarise our analysis of the high resolution phase quantification part, so we were able to show that there were different calcium silicate polymers, so C3S alite and C2S B-lite present, and the unit cell changes we were able to detect unit cell changes according to the sulfur and magnesium content. So this is an advantage of using such high resolution X-ray data. If we're going to go on and do our phase quantification modelling, as we did in the previous project, we need structural models. And if you look up structural models for the calcium silicate phases, we only find that they have calcium, silicon and oxygen in them. But if we know that we have significant amounts of magnesium and sulfur present in these structures, we need the model to show where those ions are located. So we did a lot of bond valence sums. So this is looking at detail in the bonding environment, so specifically around the calcium sites. So from the bond length data that we're able to extract from our structural modelling, we can then calculate the valence on the site. And obviously for calcium, you would hope it was 2+. And any deviations from that allowed us to look at sites that would tolerate the smaller magnesium ions substituting onto the phase. So we were able to revise our model from our high resolution data. And we found there were very subtle differences in the fits of the data, but it did improve the fit of the data. And we found this across all our samples. So we successfully used a bond valence analysis approach to revise the structural model for one of these polymorphs and allow us to predict where the foreign ions incorporate into the structure. So as well as doing our high resolution structural studies, we also used the ability of the high flux of the synchrotron source to do rapid data collection experiments and monitor hydration of these industrial clinker samples. So initially we were looking at early stages of hydration over the first 6 hours, and here we've plotted some data of a set of samples, and we used the presence of portlandite, which is calcium hydroxide. So when we saw that appearing, we knew that the hydration processes were beginning. And we found that both the presence of magnesium and sulfur influenced the hydration rate, and we showed that lower hydration rates were found between a ratio of magnesium oxide to sulfur oxide of 7.5 to 8.5. So obviously in cements, hydration goes on much longer than 6 hours. So we wanted to see if we could monitor in situ using diffraction techniques longer periods of time. And at Diamond, they have a beamline that does long duration experiments, and we successfully applied for 2 years worth of beam time to carry out these experiments. So we started them in July 2018. We set up 8 different samples hydrating. So this is our little rack here with our little capillaries in it. And once a week, they get fired into the beam and we get our data sent to us. And we can monitor what's happening on a week-by-week basis. In fact, the project went on a little bit longer than 2 years because of COVID. I'm just going to present some of the early results that we've got so far. So after 9 days of hydration, we can still see that the sulfate. Okay, sorry. So we were able to see after a few days of hydration, we still had some of the alite and B-lite silicate phases present, but we're finding the presence of some phases that we'd expect to find on hydration of clinker samples. So I should say this is just pure clinker powders that we've obtained from our industrial sponsors with water. We didn't add any gypsum calcium sulfate at this point. So we can see portlandite forming and these calcium aluminium silicate hydrate phases forming. As we increase time, so after about nearly 100 days of hydration, all of the alite, the C3S phase, has gone. We have Ettringite still present, which is quite unusual, and Portlandite. So I think this graph shows it in a bit more detail. So the time zero is not quite time zero, it's about 6 hours after we settle the experiments up. So we're already seeing some hydration products at what we've got 0 on the graph. As we increase time, we can see that the M3 polymorph, C3S polymorph, has all gone by about 9 days. The M1 is still there up till about 60 days. Portlandite is present throughout. Oh, sorry, that's belite. Sorry, that's C2S, so that's still present after 100 days. But the one that we're really interested in is this Ettringite phase. So it's present all the way through our 98 days, and I think even after a few 2 and a bit years, we're still seeing Ettringite present. So this is particularly unusual because in normal circumstances, when cement clinkers hydrate, the Ettringite will continue reacting and form a monosulfate phase. So after a few days, it shouldn't be present. We're finding Ettringite present there after many months of reaction. We haven't added gypsum into the mixture, and that's normally the sulfate source when cement clinker powders react to form the Ettringite phase. The only sulfur source in our samples comes from the actual sulfur that's been incorporated into the clinker phases. So perhaps this is somehow stabilizing the Ettringite phase. The carbonate phases that are present, they're likely to be due to some sort of CO2 absorption that would have occurred during our sample preparation because we didn't do it in a glove box. And we're finding that their hydration behaviour is different between the different clinker samples we've analysed, and we think this is due to the different elemental compositions that these clinker phases have. So just to finally sum up, we've looked at some remediation materials that have potential development for remediating potentially toxic elements in solution. And we're really now looking the next steps to develop these remediation methods for solid waste streams using mechanochemical methods. Hopefully I've shown you in all these examples that the materials do have real world applications, but having some fundamental studies gives a lot more confidence in the understanding of these materials and knowing the next steps for those developments. And in all the studies that I've presented here, they've involved a multi-technique characterization approach, so using different elemental analysis techniques, thermogravimetric analysis techniques, different diffraction methods, and putting together all these bits of information gives us a much more robust understanding of these materials. So I'd just like to finally thank all the people involved in these projects. So colleagues at the University of Edinburgh, Rebecca Ray, who carried out the Ettringite chromate project, Fee McIver-Jones, who worked on the metatorbernite and metazunarite, Margaret Graham, who's a professor in geosciences and has interests in PTs in solution, and Professor Carol Morrison, who helped us with the modelling studies. Colleagues at the Federal University of Paraíba in Brazil, so Sandro and his team, and William, whose PhD I presented in the last talk. Colleagues from Loughborough University, so Joe, who was a PhD student with me, and Sandy Dan, who started off the metatorbernite project. Colleagues at the Diamond Light Source and at ISIS for their help in setting up the experiments, and the people who helped fund the research to make it possible, and you for your attention. Thank you.
Excellent. Thank you so much, Caroline. That was a great talk.